Welcome back to Mechanical Engineering Made Simple.
It is good to be back.
You know, we spend our entire lives surrounded by machines. We drive them, we fly in them, we use them to preserve our food and keep our homes livable. We are constantly interacting with these devices, pressing buttons, turning keys, trusting them with our lives. But most of us only ever see the surface, the steel, the plastic, the user interface.
Right, the shell.
Exactly. There is a hidden narrative underneath all that hardware.
Yeah.
I like to call it the invisible machine.
The invisible machine. I like that. You were referring to the energy itself, aren't you? The fluid reality that actually does the work.
Precisely. We see the piston move or the turbine spin, but we rarely stop to think about the journey of the energy driving it. It's like watching a puppet show and forgetting about the strings or, the hands pulling the strings.
That's a great analogy.
So today's deep dive is going to be a little different. We are going on a walkthrough story. We aren't just going to read definitions from a textbook or, cite formulas in a vacuum.
I hope not.
We are going to follow a single unit of energy, a spark, if you will, from the moment it is locked inside a chemical bond, through the violent explosion of combustion, into the mechanical struggle of an engine, and finally, to the ultimate challenge of getting rid of the waste heat.
It is a journey from order to disorder, effectively.
Yes.
It is the story of the universe in microcosm.
It really is.
And to do this properly, to really do justice to this narrative, we have pulled together a stack of heavy-hitting sources. We have got detailed analysis on the thermodynamics of combustion, the rigorous laws of equilibrium, engineering cycle analysis, from gas turbines to steam, and the modern, somewhat philosophical engineering concept of exergy.
And we're even going to shrink down to the microscale to look at how we cool computer chips.
Yeah.
So imagine the backdrop for today isn't a recording studio. I want you to close your eyes. Imagine we are in a high-tech engineering lab.
Yeah.
On one side, you have a massive combustion chamber roaring away, containing a controlled explosion. In the middle, a steam turbine spinning at thousands of RPM. And on the far bench, a microscope looking at a silicon chip.
A fitting setting, because the physics governing that massive turbine are surprisingly similar to the physics governing that tiny chip.
Really? How so?
It all comes down to how heat moves and how we can or cannot control it. Whether you are generating gigawatts for a city or trying to keep a processor from melting while playing a video game, the rules are the same.
So let's light the fuse. We are starting with our first section, the spark. We have all seen fire, it's elemental. But a common question online, one that pops up constantly on forums is fire just hot air? Or what actually happens to the fuel? When we say we are burning gas in a car, what is physically going on at the molecular level?
At a fundamental level, combustion is an oxidation process. It is almost always exothermic, meaning it releases heat.
Right, out. It pushes heat out.
Exactly. But to understand it, you have to look at the fuel. You have chemical energy stored in the bonds of a fuel, usually a hydrocarbon like petrol, diesel, or methane. Picture these molecules. They are chains of carbon and hydrogen holding hands very tightly. They are stable, happy, and just full of potential energy.
So they're like a coiled spring, just waiting.
Exactly. A perfectly coiled spring. And then you introduce an oxidant, typically the oxygen in the air. Oxygen is aggressive. It wants those electrons. But the fuel bonds are strong.
Okay.
So you need a catalyst, a kickstart. That's your spark plug or your compression heat. When you introduce that ignition source, you are essentially forcing those hands to let go. You are shattering the existing structure.
You're breaking the bonds apart. It's a violent divorce.
Precisely. You're breaking the bonds of the fuel and the oxygen. But here is the magic trick of the universe. You then form new bonds in the products. The carbon grabs the oxygen to form carbon dioxide. The hydrogen grabs the oxygen to form water vapor. The key insight, the reason fire is hot, is that the energy required to break the old bonds is less than the energy released when the new bonds form.
Okay, I see. So it takes a little energy to break them apart, but you get a huge payout when they snap back together into new things.
Correct. That surplus energy, that is the heat you feel. That is the kinetic energy of the molecules flying apart. That is the explosion.
So it's a trade. We trade complex hydrocarbon molecules for simpler CO2 and water, and we get a payout in thermal energy.
That's the transaction.
But is there a perfect way to do this? I see the term stoichiometry come up a lot in the text. It sounds like a Greek tragedy.
It does, doesn't it? Stoichiometry is essentially the perfect recipe. Imagine you are baking a cake. You need exactly the right amount of flour for the amount of eggs you have. If you have too much flour, it's dry. Too many eggs, it's a mess. In combustion, the stoichiometric condition is when you have exactly enough oxygen molecules to react with every single fuel molecule with absolutely nothing left over.
No wasted fuel, no wasted air.
In theory, yes, an equivalence ratio of 1. But here is where it gets really interesting and where the sources point out some real-world complications that most people don't think about.
Okay.
You might think, okay, if I have the perfect mixture, I'll get the maximum possible temperature.
That makes intuitive sense. If you aren't heating up extra air that isn't participating in the reaction, like if you run lean with too much air, shouldn't the flame be hottest at that perfect ratio?
You would think so. It's logical. But reality has a speed limit. It's called dissociation.
Dissociation.
When the temperature gets high enough, we are talking thousands of degrees. Kelvin, the products, the carbon dioxide and the water vapor, they don't just stay stable. The environment is too chaotic. They start to split back apart.
Wait, they unburn.
In a sense, yes. The violence of the heat is so intense that the carbon dioxide splits back into carbon monoxide and oxygen. The water splits into hydroxide and hydrogen.
Yeah.
Now, remember what we said earlier. Forming bonds releases energy, but breaking bonds...
Breaking bonds absorbs energy. It costs energy.
Exactly. It is endothermic. So this dissociation process acts like a chemical brake on the temperature rise. It sucks up some of that thermal energy you just released to rip the molecules apart again.
So even with a perfect mixture, you hit a ceiling, the fire gets so hot it defeats itself.
That's it. You've nailed it.
That is fascinating. It's like a self-limiting system. Nature says, okay, that's hot enough.
Precisely. And when we try to calculate these temperatures in the lab, we have to look at whether the process is adiabatic.
Adiabatic. That's one of those $5 engineering words. Let's unpack that for the listener.
It just describes a process where no heat is lost to the surroundings. Imagine a combustion chamber wrapped in a perfect magical blanket.
A perfect insulator.
Right. In a theoretical adiabatic combustion chamber, all that chemical energy stays in the gas, raising its temperature to the absolute maximum. But in a real engine, the walls are made of metal, they're cold, there's coolant flowing through channels in the block. Heat is escaping constantly, so the actual peak temperature is always lower than the adiabatic flame temperature.
It's the difference between the theoretical maximum speed of a car in a vacuum versus driving it on a road with wind resistance and friction.
That is a great analogy, a perfect one. And speaking of the gas itself, I noticed in the math sections of these sources, there are a lot of references to two variables, C sub V and C sub P.
Right, specific heats. I always found this a bit confusing. Why do we need two different variables for specific heat? Isn't heat just heat?
You would hope so, but gases are tricky. Specific heat is a measure of how much energy is needed to raise the temperature of a substance by 1 degree. But a gas behaves differently depending on its container. C sub V is specific heat at constant volume. Think of a rigid steel box. You heat the gas, the pressure rises, but the box doesn't move. All the energy goes into temperature.
Okay, so sealed container and C sub P.
C sub P is specific heat at constant pressure. Think of a cylinder with a piston that can slide up and down like in an engine. As you heat the gas, it expands. It pushes the piston up.
So the gas is doing work while it's heating up.
Exactly. And because it's doing work pushing that piston, it is using up some of the energy you're feeding it. So to get the temperature to rise by that same 1 degree, you have to put more energy in.
Ah, I see.
You have to feed the temperature rise and the work output. That is why C sub P is always higher than C sub V.
That makes perfect sense. One is just heating, the other is heating plus lifting weights.
A very good way to put it. And the ratio of these two, often denoted as K or gamma, is vital for calculating engine efficiency. It tells us how springy the gas is.
So we have had our explosion. We have generated this massive spike in temperature and pressure. The molecules are dissociated, then reassociated, vibrating like crazy. Now we have to play by the rules.
The unbreakable rules.
Section 2, the rules of the road. I'm talking about the laws of thermodynamics.
The laws that govern the universe, or at least the laws that govern how we interact with energy. These are the laws that tell us what is possible and what is a fantasy.
And the ones that crush the dreams of every inventor trying to build a perpetual motion machine in their garage. Let's start with the first law.
The first law is the law of conservation. It is the accountant of the universe, the auditor. It simply states that energy cannot be created or destroyed, only change from one form to another.
Right.
If you look at a closed system, the change in the internal energy denoted as E2 minus E1 must equal the net heat added to the system minus the work done by the system.
So energy change equals heat minus work. E2 minus E1 equals Q minus W. You can't get something for nothing.
Precisely. If you want workout, you have to put energy in, either as heat or potential energy. The bank account must balance. There are no overdrafts in physics.
None at all.
If you see a machine that claims to output more energy than it takes in, the first law says, look for the hidden battery.
Right. Find the cord plugged into the wall. But if the first law is the accountant checking the books, the second law feels like the tax man.
The tax man, or perhaps the traffic cop. I like that. The first law says you can convert energy. It doesn't care about the direction. It thinks turning smoke back into a log is just as valid as burning a log into smoke as long as the energy matches. The second law tells you the direction that conversion can happen. It introduces the concept of entropy.
Entropy, the measure of disorder. But it's more than just a messy room, isn't it?
It is, yeah. It's a very deep concept. Ideally, think of it as unavailability. The second law dictates that heat naturally flows from a hot body to a cold body. Never the other way around, unless you force it with external work.
Like a refrigerator.
Exactly. And the seemingly simple observation that coffee gets cold, it doesn't spontaneously boil, has massive implications for engineering. It means that whenever we try to convert heat into work, we are fighting a losing battle against disorder.
This is where we get into the concept of irreversibility, right?
Correct. Real processes, friction, turbulence, mixing, heat transfer across a temperature gap generate entropy. We call this S-subgen, or entropy generation.
S-gen.
Every time you generate entropy, you are permanently destroying the potential to do useful work. You are taking organized energy and making it disorganized. You are taking a stack of sorted playing cards and shuffling them. You still have 52 cards, that's the first law.
Right, conserved.
But you can't play the game anymore, that's the second law.
That is a depressing but effective analogy. And this leads us to the ultimate limit, the speed limit of the universe. The Carnot limit.
Sadi Carnot, a French engineer in the 1820s. He was thinking about steam engines before we even really understood what heat was.
That's amazing.
It is. He realized that the efficiency of a heat engine, any engine that turns heat into work, depends entirely on the temperatures it operates between. No engine can be more efficient than a reversible one operating between a high-temperature reservoir, T sub H, and a low-temperature reservoir, T sub L.
So TH and TL. The hot side and the cold side. And the formula for that limit is surprisingly simple, considering how powerful it is.
It is elegant. The maximum theoretical efficiency is 1 minus the ratio of the low temperature to the high temperature. So efficiency equals 1 minus T sub L divided by T sub H.
So to get better efficiency, if you look at that math, you really only have two knobs to turn. You either make the hot side hotter or the cold side colder.
Exactly. Those are your only options. And think about the cold side T sub L. That is usually the environment. The air outside your car, the river water cooling a power plant.
Right.
That is around 300 Kelvin, maybe 27 degrees Celsius. We can't lower the temperature of the planet just to make our engines better. We are stuck with T sub L.
So the only way is up.
The only way is up. That is why engineers are obsessed with pushing T sub H, the combustion temperature, higher and higher. The hotter we burn, the more efficient we can theoretically be. That is why we use exotic superalloys in jet engines, so they don't melt while we chase that high Carnot efficiency.
Okay, so we have the fuel and we have the rules. Now, let's build the machine. Section 3, turning heat into motion. We are talking about engineering cycles.
This is where the rubber meets the road. We use what we call a heat engine. As we established, this is a device that takes thermal energy, converts some of it to work, and, this is crucial, rejects the rest to a sink.
Always.
You cannot convert 100% of heat into work. The second law forbids it. You always have to pay the tax to the cold reservoir.
Let's walk through the big ones, the workhorses of the modern world.
Yeah.
First up, the steam plant, the Rankine cycle. This is what keeps the lights on in most of the world.
The Rankine cycle is the backbone of global electricity. It uses water as the working fluid. Let's trace the path. You have a boiler that turns liquid water into high-pressure steam. That steam expands through a turbine. As it expands, it hits the blades, spinning them. That's your work output. Then the steam goes into a condenser where it turns back into liquid water, rejecting heat to the environment. Finally, a pump sends it back to the boiler to start again.
Why water? Why not air? Or mercury?
Water is magical, but for the Rankine cycle, the secret sauce is the phase change. When steam condenses back to water, its volume collapses. Liquid water is almost incompressible.
Right, you can't really squeeze it.
You can't. It takes very little energy to pump liquid water up to high pressure. If you tried to compress gas, it would take a huge amount of energy. But pumping water is cheap. In the Rankine cycle, the backwork ratio, the energy cost to run the pump, is tiny, maybe 1 or 2% of the total output.
So you get almost all the turbine work as profit.
Exactly. It's an incredible thermodynamic bargain.
Now compare that to the engine hanging off the wing of an airliner, the gas turbine, the Brayton or Joule cycle.
Very different beast. Here, the working fluid is air, and it stays a gas the whole time. It never becomes a liquid. You suck air in the front, compress it, that's the compressor. Then you spray fuel into it and burn it, that's the combustor. Then that hot, high-pressure gas roars through the turbine.
And unlike the steam plant, the compressor here isn't cheap to run.
Not at all. Compressing gas is hard work. Imagine trying to squeeze a balloon versus pumping water. In a gas turbine, the compressor is a glutton.
A glutton, I like that.
It consumes a huge chunk of the power generated by the turbine, sometimes up to half or even more. The turbine has to drive the compressor just to keep the cycle going. The rest is what we use for thrust or shaft power.
That's amazing. Half the engine's power is just used to keep the engine breathing.
It is the cost of doing business with a gas. It's the price of admission.
The sources mentioned pressure ratios being a big deal here.
Huge. Modern gas turbines operate at pressure ratios of 20 to 1, 30 to 1, or even higher. That means the air is squeezed to 30 times atmospheric pressure before combustion. High pressure ratios give you high power density, a lot of power in a small, light package. That is why they are perfect for aircraft, where weight is everything. A steam plant is efficient, but it is heavy. You can't fly a steam plant.
Now here's where it gets really cool. The aha moment in power generation, the combined cycle. This feels like the Avengers team-up of engineering.
It really is. This is the smartest trick in the book. You take a gas turbine, which runs very hot exhaust temperatures, can be 600 degrees Celsius or more.
Okay.
Usually that heat would just be wasted, blown out the stack, but 600 degrees is plenty hot enough to boil water. So in a combined cycle, you use that hot exhaust to boil water for a steam turbine loop.
So the waste of the first engine becomes the fuel for the second engine.
Exactly. You are stacking the cycles, you get the high T sub H efficiency of the gas turbine and the low temperature heat rejection of the steam cycle. This widens the gap between your high and low temperatures, pushing the total efficiency way up, sometimes over 60%, which is unheard of for a single engine.
Incredible. And briefly, for everyone driving to work today, the internal combustion engine, the Otto cycle.
The Otto cycle is what happens in your petrol car. Intake, compression, combustion, exhaust. The key distinction here is that combustion happens ideally at constant volume.
What does that mean, constant volume?
The piston is at the top of its stroke, it's stopped for an instant, the spark fires, and boom, pressure spikes instantly before the piston has a chance to move down. It is a violent kick.
And the efficiency here depends on how much you squeeze the compression ratio.
Right. The more you compress the air before igniting it, the more work you get out. But if you compress it too much, the fuel might self-ignite before the spark due to the heat of compression. That's called knocking.
The pinging sound.
That's the one. So there is a limit based on the fuel's octane rating.
Okay, so we're generating power, we are spinning shafts, but let's pause and look at the quality of what we are doing. Section 4. It's not just quantity. It's quality. We need to talk about exergy.
Exergy is one of the most important yet least understood concepts in engineering. We usually talk about energy conservation. Energy is never lost.
Right.
But if energy is conserved, why do we have an energy crisis? Why can't we just reuse the energy from the exhaust pipe over and over again?
That's the question. We didn't destroy the energy, but we destroyed something else.
We destroyed the quality. Exergy, sometimes called availability, is a measure of the maximum useful work that can be done by a system as it comes into equilibrium with its environment. We compare everything to the dead state.
The dead state. Sounds ominous, like a post-apocalyptic wasteland.
It's just the environment. Pressure of 1 bar, temperature of 25 degrees Celsius, usually denoted as T sub 0. Once your system reaches that state, it has zero exergy.
So explain that.
Think about it. A bathtub full of lukewarm water might contain a lot of thermal energy joules, but you can't run an engine off it because it's the same temperature as the air. It has energy, but zero exergy. It has no potential to do work relative to its surroundings.
So while energy is conserved, exergy is destroyed.
Yes. That is the tragedy of thermodynamics. Every time you have friction or mix two fluids or, and this is the big one, transfer heat across a temperature difference, you destroy exergy.
Okay.
If you take high temperature steam and just let it cool down to warm water without running a turbine, you have destroyed that potential. You are taking high quality energy and degrading it into low quality heat.
The sources bring up a theorem here that links this back to entropy, the Gauss-Stodela theorem.
This is a beautiful piece of physics. It puts a price tag on our mistakes. It states that the lost work, the work you could have had but didn't get, is directly proportional to the entropy generation. The formula is W sub lost equals T sub 0 multiplied by S sub gen.
Work lost equals T sub 0 times S sub gen. So the temperature of the environment times the mess you made equals the opportunity you wasted.
Exactly. This gives engineers a target. We call it entropy generation minimization, or EGM. Modern design isn't just about efficiency in the old sense of burning less fuel. It is about identifying exactly where entropy is being generated in a component, say a heat exchanger tube, and redesigning it to minimize that S subgen.
Can you give us a concrete example of that trade-off? Because usually we think friction is bad, heat transfer is good.
Sure. Think of a heat exchanger tube. You want to transfer heat from the fluid inside to the fluid outside. To do that well, you want the flow to be turbulent. Turbulence mixes the fluid and grabs the heat.
Right.
So you might make the tube very long or narrow to create that turbulence. But turbulence creates friction. Friction causes a pressure drop, which means your pump has to work harder.
So you have a conflict. The thing that helps heat transfer also hurts your pump.
Exactly. And both generate entropy. Friction generates entropy bad, but poor heat transfer also generates entropy because of the large temperature difference, also bad. EGM helps you find the optimal diameter where the sum of those two evils is minimized. You are balancing the entropy of friction against the entropy of heat transfer.
That is incredibly nuanced. It's not just make it bigger or make it smaller. It's find the balance point.
It is optimization in its purest form.
So we have extracted the work, we have minimized our losses using exergy analysis, but we still have heat left over. And in some cases, like electronics, heat isn't a resource we are trying to catch, it's the enemy.
It's the absolute enemy.
Section 5, dealing with the heat.
This is a huge field. You have a computer chip the size of a fingernail generating as much heat flux, that's watts per square meter, as a nuclear reactor core. It is intensely concentrated.
Wow.
If you don't get that heat out, the silicon junction temperature rises, the transistors leak current, timing errors happen, and eventually the chip physically melts or cracks.
I love the analogy the sources use here to explain how we move this heat. They compare heat flow to electricity.
Yes, the thermal resistance network. It is exactly like Ohm's law. In electricity, voltage equals current times resistance, V equals I times R. In heat transfer, we have an equivalent. The temperature difference delta T equals the heat flow rate Q times the thermal resistance R.
So if you want to keep the chip temperature low, which is like keeping the voltage low, but you have a high heat flow, high current, you have to lower the thermal resistance.
Exactly. You want the path of least resistance for that heat to escape. And we have 3 modes to do that: conduction, convection, and radiation.
Let's break them down. Conduction. This is the heat moving through solids.
That's Fourier's law. Heat moving from the silicon die through the thermal paste into the copper base of the heatsink. The resistance here depends on the thickness of the material and its thermal conductivity, K. Copper has a high K, which is why we use it. Plastic has a low K, which is why it's an insulator. You want the heat to sprint through the solid material.
Then convection. That's the air moving over the heatsink fence.
Right. And here we get into the dimensionless numbers that engineers love. We need to know how effective the air is at grabbing the heat. We use the Nusselt number.
The Nusselt number.
The Nusselt number tells us how good the convection is compared to just stagnant conduction. A high Nusselt number means the air is scrubbing that heat away effectively.
And to get a high Nusselt number, you need flow.
Yes, and that brings us to the Reynolds number. This tells us if the airflow is smooth, laminar, or chaotic, turbulent. Turbulent flow is much better for cooling because it mixes the air, bringing fresh, cool air into contact with the fins. But it requires louder, stronger fans.
And the sources mention natural convection versus forced convection. Forced is using a fan. Natural is doing nothing.
Natural convection is passive. It is what happens when your computer is silent. The air near the fins gets hot, expands, becomes less dense, and rises.
Buoyancy.
Buoyancy drives the flow. It acts like a weak pump. We use the Rayleigh number to describe this flow strength.
And there's another number for the fins themselves, right? The Ehrenbos number?
Yes. The Ehrenbos number is specific for those vertical fins you see on heat sinks. It helped answer the question, how close can I pack these fins?
Because you would think more fins equals more surface area equals better cooling.
That is the trap. Air is viscous, it's sticky. If the fins are too close together, the boundary layers of the air, the slow-moving air clinging to the surface, merge from both sides.
Okay.
They block each other. You effectively choke off the flow. The air can't get in to grab the heat.
It's like trying to breathe through a straw that's too thin.
Exactly. But if they are too far apart, you are wasting valuable space where you could have put more surface area. The Ehrenbos number helps you find the sweet spot for spacing, where you maximize surface area without choking the flow.
And what about radiation? I usually think of that as something the sun does. Does my computer really radiate heat?
In electronics cooling, it is often ignored, but it shouldn't be. Every surface radiates heat based on its temperature and emissivity, how black it is in the infrared spectrum.
Oh.
It depends on the Stefan-Boltzmann constant. For a black anodized heat sink in a computer case, radiation can account for a significant chunk of the cooling, maybe 10 to 15%, especially if the fan fails or runs slow. It is the cooling of last resort.
There was one specific detail in the text that I found really interesting: spreading resistance.
Yes. This is a geometric problem. Imagine you have a tiny chip, say 1 square centimeter, producing 100 watts. You clamp a big heat sink on top of it that is 10 centimeters wide.
Okay.
You might assume the whole heat sink is working, but the heat has to flow from that tiny contact patch and spread out to fill the base of the big heat sink.
So the corners of the heat sink might be cooled because the heat hasn't reached them yet.
Exactly. That spreading action creates a bottleneck. It's like a crowd of people trying to get out of a stadium through one exit door. The resistance is high at the door.
So how do you fix it?
You need a thick base. The math shows that the heat spreader needs to be thick enough to allow that flow to open up, to diverge before it hits the fins.
Yeah.
A rule of thumb from the text is that the spreader needs to be 3 to 5 times thicker than the square root of the heat source area to be effective. If it's too thin, the heat just shoots straight through and ignores the outer edges of the sink. You are carrying dead weight.
And then there is the interface itself, contact resistance.
This is microscopic.
Mm-hmm.
You put a heat sink on a chip, and to your eye, it looks like they are touching perfectly, flat on flat. But under a microscope, the surfaces look like mountain ranges. They are rough. They only touch at the peaks, the asperities.
So most of the gap is actually just air.
Yes, and air is a terrible conductor of heat. Its thermal conductivity is tiny, so you have these tiny bridges of metal where heat flows well and huge canyons of air where heat flows poorly.
And that's where the thermal paste comes in.
That is why we use thermal paste, the gray goop.
The gray goop.
It fills in the valleys between the asperities, replacing the air with a conductive material. It maximizes the contact area. Without that paste, your expensive cooler is practically useless because the heat can't bridge the gap.
Okay, we have heated things up, we have cooled them down, but what if we want to get really cold? Section 6, the cold frontier, refrigeration and cryogenics.
Now we are flipping the script. A heat engine takes heat and makes work. A refrigerator takes work and moves heat from a cold place to a hot place.
Uphill.
It is pushing heat uphill, against the natural flow dictated by the second law.
Correct. We are fighting the tax man. And because of that, we don't talk about efficiency. Efficiency is always less than 1, but a fridge can move more energy than it consumes.
Right.
So we talk about the coefficient of performance, or COP.
And the COP can be greater than 1, right? Which
Yeah.
sounds like magic. I put in 1 watt and I get 3 watts of cooling.
It does.
It does sound like magic, but remember, you aren't creating the cold, you are moving the heat.
Yeah.
If a heat pump has a COP of 3, it means for every 1 joule of electrical work you put in, you move 3 joules of heat out of the fridge. You are a heat mover, not a heat maker.
But when we get down to cryogenics liquefying gases like nitrogen or helium, it gets harder. The COP drops.
Much harder. The Carnot limit bites you here. Remember the efficiency formula. 1 minus TL over TH. Well, for a refrigerator, the work required is proportional to the difference between the temperatures divided by the cold temperature squared.
Okay, that sounds bad.
It is. As T-sub-L gets closer to absolute 0, the work required to remove even a tiny amount of heat becomes enormous. The price of cooling skyrockets.
The text mentions the Stirling cycle in this context.
The Stirling cycle is fascinating. It uses a regenerator, a thermal sponge, basically. It's a wire mesh inside the engine.
A sponge.
You compress the gas, it gets hot. The regenerator absorbs that heat. You expand the gas, it gets very cold. And on the way back, the regenerator gives the heat back. It recycles the thermal energy internally. It's critical for reaching those cryogenic temperatures efficiently without needing massive compressors.
And the design of heat exchangers becomes life or death here.
Absolutely. In a power plant, if your heat exchanger is a bit inefficient, maybe you have a 5-degree difference instead of 2 degrees, you lose 1% of fuel efficiency. No big deal. In cryogenics, because the temperature difference delta T represents such a huge loss of exergy at low temperatures, a slightly inefficient heat exchanger can completely stop the machine from working. If the incoming gas isn't pre-cooled perfectly by the outgoing gas, the cycle fails. The exergy loss is magnified at low temperatures.
We have covered a lot of ground. Equilibrium, steady states, cycles. But the world isn't always stable. Section 7. Non-equilibrium.
This is the frontier of thermodynamics. Real life rarely sits in equilibrium. Things are flowing, changing. The sources mention Onsager's reciprocal relations.
Reciprocal relations. That sounds complex. What does that mean in plain English?
It means that different forces are coupled. We usually think in silos. Temperature difference causes heat flow. Voltage difference causes current.
Right. Cause and effect.
But Onsager showed that these forces can cross over.
Cross over.
Yes. A temperature difference can cause mass to move diffusion. That's the Soret effect. If you have a mixture of gases and you heat one side, the heavy molecules might migrate to the cold side. Or a voltage difference can cause a temperature difference, the thermoelectric effect or Peltier effect.
So everything is connected. You push on nature in one way, and it reacts in multiple ways.
Exactly. It shows the deep interconnectedness of physical phenomena. You cannot treat heat, electricity, and mass flow as completely separate silos. They are all just fluxes of energy and entropy-seeking balance.
So let's bring this all home. We started with a chemical bond snapping in a hydrocarbon molecule.
We released that energy, creating a high-temperature gas. We fought the dissociation that tried to limit our temperature. We understood the violence of the molecular divorce.
You ran that gas through a cycle, maybe a gas turbine, maybe a piston engine, always obeying the first law of Countsy and the second law of Taxman. We realized we can't get something for nothing, and we can't break even.
We hit the Carnot limit, extracting as much work as the temperature reservoirs allowed.
Right.
We analyzed our losses using exergy to see where we were destroying usefulness. We optimized our tubes and flows.
And finally, we managed the waste heat using fins, fans, and thermal paste to coax that entropy out into the environment so the machine doesn't melt. We navigated the resistance network.
It is a continuous, elegant struggle against the arrow of time.
And that leads us to our final thought. The sources hint at a design philosophy for the future.
Yes. For a long time, engineering was about energy efficiency, just saving fuel. But the future is entropy generation minimization. It's a subtle shift. We need to design systems, from power plants to laptops, that fight the creation of disorder. We want to guide energy through our machines as gently as possible, preserving its quality for as long as possible. The engineer of the future isn't just an energy manager. They are an entropy architect.
An entropy architect, I love that. It turns engineering into an art form. Well, that wraps up our walkthrough of the engine of the universe.
A pleasure to walk through it with you.
If you enjoyed this deep dive, and you want to see some of these principles in action, maybe watching us try and fail to build a Stirling engine, or visualizing a heat sink in a wind tunnel. If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.